So we have spent a couple of days in the computer lab looking at the area under curves using the rectangle, upper and lower rectangle method, the trapezoid method, and the Simpson's method. And then finally we use the Riemann method. And in all these cases we were able to obtain approximations to areas under curves using a number of rectangles, trapezoids, or regions with parabolic tops. We found that as we increased the number of regions, the error got less and less. And then in the final part of our laboratory work, we looked at the Riemann sum, which is this sum right here, and we found that as we let the number of intervals get larger and larger and larger, or if we put the limit as n goes to infinity in front of this summation, we got the exact area. So I hope you were convinced in the last part of that lab that as we took more and more of the Riemann rectangles, the rectangles that had this height and this width, and then we took the sum of all those n sums, but then we let more and more rectangles enter in and took the limit, that we got what we called the exact area under the curve. So this exact area under the curve, actually we give a special name to that, and it's called the definite integral. What we want to do in this video is not just define that this limit right here is the definite integral, but the definite integral that has this other notation, but we want to find a way to calculate the value of the definite integral so that we do not have to go through the limit definition to find our values. So let's start the process of finding a way to calculate this definite integral. And what we'll find out is that it turns out to be this difference, capital F of B minus capital F of A, but we're going to have to, on the next blackboards, define what we mean by the function capital F. We're going to have to do that very specifically. So let's move to the next blackboard. So in the lab we saw that this limit was the exact area, and what we have just said is that another name for that limit is this notation, the integral from a to b of f of x dx. What we're going to show is that we can calculate this definite integral as capital F of b minus capital F of a. So let's define the function capital F and set up the proof of this theorem. So if we define our function little f, this function right here under the integral sign, to be a continuous function, and if we define this function here, capital F, to be such that its derivative is the function lowercase f, then we have this result, that all three of these quantities are equal. And the most important point for purposes of calculating is that we can calculate, instead of having to use this limit definition here, we can use the this to calculate the value of our integrals, which in many cases is the area under the curve. So let's prove this theorem on the next couple of blackboards. So we're going to start off by defining how the interval AB is divided up. It's going to be divided up using what we call a partition. We're going to call the left endpoint x sub 0. We're going to call the right endpoint b x sub n, and then we just have an unspecified number of x values between x0 and xn, with the only requirement is that they're in each one is to the left of the one that follows it. So on the interval AB, on the number line, it would look like this. So the values, the subscripted values move from left to right. So here's our x0, x1, x2, x3. And notice that the spacing between them is not the same. They can be spaced anywhere apart. We've also put this break in the number line right here to signify that there's an arbitrary number of values between this x4 and this xn minus 1. The most important thing to note here really is that the interval, or the values x0 to xn, or x1 to xn minus 1, are arbitrarily placed between the endpoints. So we're setting it up so this is a most general case. The x1 to xn minus 1 can be put anywhere on the interval, and we do this often when we're proving a theorem. We don't want to restrict how we're placing our x values on the interval, because we want to be able to prove our theorem in the most general setting possible, and this most general setting has an arbitrary spacing of these values between x0 and xn. Okay, so let's go to the next step on the next blackboard. Our strategy in this proof, in verifying that this expression, that this limit is the same as this capital F of B minus capital F of A, is going to be to start with this expression, and we're going to then show that it is equal to this expression, this limit expression. So we're going to start with capital F of B minus capital F of A. I'm going to start with this. So we've stretched out the difference F of B minus F of A into what we call a telescoping sum. It's called a telescoping sum because if you look at this a little more carefully, you see that we've subtracted and added the same expression throughout, and so the only terms that are really in here are f of xn minus f of x0. So it really is the same as what we started with. But since we're trying to get this expression right here to look like a sum, that is, we're trying to get it to look like this, then you can perhaps see why we want to put a large number of terms in here. In fact, this is an expression involving n terms. So let's take all of these differences that we have. So all of these difference expressions we're going to, on the next blackboard, write in a slightly different way. Let's first take a little bit of a sidetrack and point out this theorem that's proven, or at least stated and justified, on page 100 of your textbook. It's called the mean value theorem, and it says that if you have the difference of two function values, f of b minus f of a, that you can rewrite that as f prime of c times b minus a, f prime being the derivative of f, for some c in the interval ab. And so we're going to use that, this mean value theorem, for each one of these expressions. So I've just picked one of them out, arbitrarily, f of x of n minus 2 minus f of x of n minus 3, and using the mean value theorem we can say that that's equal to the derivative of this function, so that's capital F prime, at some value between here and here, times the difference of those two values, x sub n minus 2 minus x sub n minus 3. And that value between we're going to call x sub n minus 2, and we're going to put an asterisk on it to designate that it's between these two values. That it's between here and here, just like the C right here was between the A and the B. The C was between this A and B, and now down here our x sub n minus 2 asterisk is between this value and this value. So we're going to make that change to every term in this sum, to every single one. Every one of these differences we're going to rewrite in this structure right here. So let's do that on the next blackboard. So we've rewritten our original sum f of b minus f of a in this different notation using the mean value theorem notation for each one of these terms. And notice that we use this dot 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 here called an ellipsis to designate that the pattern continues. Now, if you remember in the statement of our theorem, we had this requirement that capital F's derivative is little f, and we're going to use that in every single one of these expressions we've written to write them in the little f notation. That's going to get us a lot closer to being able to represent what we started with in this form, because now we've written things with little f in them. At the same time, let's also take these expressions, these different expressions, and write them in a delta x notation. So this one we're going to call delta x sub n minus 2, and this one here we're going to call delta x sub 1. So rewriting, we get this. So we've written each one of these capital F primes in their F notation, and each one of these differences in their delta x notation. Now, it may not be clear yet, but this expression that we have on this line is actually very close to where we want to be, because it can be written in summation notation like this. Right, because summation notation is just a shorthand way to write an expression of this type. It says, what is our starting subscript 1? So we first put 1 in place of I here and here, and that gives us this term. Then we put the next value in for I, which is 2, and we keep on doing that till we eventually get to the value n minus 1. So first we get all the dot 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 terms, then we get the n minus 1 term, and then we stop putting in for our subscript I here and here. The last value we put in is n, and that gives us this term. So we've got a much more succinct way of writing this expression, and it is just this way that we write it. And if we look back to the what we were trying to prove, we see that, we've now got it looking just like this. So we've taken our f, capital F of B minus capital F of A, and we've changed it into this. So we're just a half a step away from proving our theorem. So here, how we get to the final step, which is to show that they are equal if we put the limit in front, is we look back to what we did, actually starting at this step. We could have, at this point right here, have made this partition for any n values we want. So we could have split up the interval between a x0 and b xn with as many points n as we want. So we could have done that as n got bigger and bigger and bigger as the limit went to infinity. And it's also true that when we rewrote our difference, our original difference, f of b minus f of a, and we split it up into n terms, the number of terms n could have been as large as we want, or in a mathematician's language, what we have shown applies if n is as big as we want, or it applies as we take the limit as n goes to infinity. So, just wrapping up, what we have shown is this. This expression is the same as this expression, and since n could be as large as we want, it's that expression with the limit n going to infinity, or getting as large as we want. So we have proven the theorem, and what the theorem allows us to do is it allows us to calculate these limits, which we spent a lot of time in the computer lab using computer techniques to figure out. It turns out that when we have this, we know the relationship between capital F and little f, or we know the antiderivative of little f, we can just do this very simple calculation right here. And so let's show that by a couple of examples on blackboards that follow. So suppose we want to find the area under the curve y equals x squared on the interval 0, 2. So we want to find the area of this region right here. This region shaded in blue. And we can see that our area is quite a bit less than the area of this 4 by 2 rectangle, which would be have an area of 8, and it's also less than half the area of that rectangle with area 8, 4, because as you can see the shading is below this diagonal line that divides the rectangle in half. It turns out that if we use the limit of Riemann sums, in other words this, doing it the long-handed way, we can actually take that limit, and we'll show that on another video how to do this. We get a limit of 8/3, but that's a pretty involved process. It's 3 or 4 blackboards long. So let's do the alternate way of finding this area under the curve using this that we've just proven. The area, actually the definite integral only gives the area when the function is above the x-axis, as it is in this case. But the area is the integral or definite integral between the two x values, 0 to 2, of the function, and the function is x squared. So all we have to do is find the capital F. So we ask the question, what capital F function is such that its derivative is this x squared? And that's an easy question to answer if we think about it a little bit. It is just this function, right? X cubed over 3, because if we apply the power rule to that, if we apply the power rule to x cubed over 3 and differentiate it, we bring the power down. That cancels the 3 in the denominator. We reduce the power from 3 to 2, and that gives us the x squared that we want, the x squared under the integral sign. So the result of this integral, this antiderivative, should be x cubed over 3, and we first plug in 2, and then we plug in 0. We first plug in this is our b. We first next plug in this is our a. And the way we designate that is to draw a vertical line and put a 0 here and a 2 here. And so that is equal to, first we plug in 2 to x cubed over 3, so that gives us 2 cubed over 3, and then we subtract, plugging 0 into it, 0 cubed over 3, and that is our 8/3. So that's a really fast way to get this result that we got earlier here using this long-handed method that we didn't actually show all the steps, but it's quite a bit longer than what we showed here. So finding areas under curves when functions are above the x-axis is as simple as finding the so we should note that we got our answer very easily, as easily as knowing, or easy when we can find the antiderivative of our function, and then we can get the result pretty quickly, very quickly. We should note, though, that it's when it's possible to get the antiderivative of our function x cubed over 3 here and from the function x squared, finding areas when it's the function above the x-axis, or finding definite integrals in the more general case is very easy. However, we can never discard this technique because, as it turns out, antiderivatives in general are very difficult to find. While we can find the derivative of any function using our power rule, product rule, quotient rule, chain rule, finding antiderivatives, the function does not have to be very complicated for us, for it to be actually impossible to do. So I'll just give a quick example. So here, this function 1 over 1 plus x cubed, pretty easy to graph, but there is not an antiderivative for that function. So if we had that problem as an application problem, we needed to find that area to solve an application problem, we would have to revert back to this method. We're not generally going to be able to take the limit as n goes to infinity, so we just get a lot of terms. And as we saw in the computer lab, if we get lots of terms, then we get we can get very good accuracy. In fact, we can get it as accurate as we want. We just have to set up a computer to give us enough terms. So let's recap what we've done in this video. We've gotten what we call the fundamental theorem of calculus. The first fundamental theorem of calculus is an extremely important result. It allows us to find definite integrals, which are in many cases areas under curves. These expressions, these limits, in a much, much simpler way, capital F of B minus capital F of A. The only requirement is that we have to know this function, capital F, the antiderivative of our function. We went through the proof of doing that. We arbitrarily divided up the interval a to b, x0 to xn, into n pieces. Those n pieces were arbitrarily placed, so it was the most general setting. The number of pieces n could be as large as we want, which turns out to be important later because that's how we can take the limit as n goes to infinity. We took our sum, capital F of B minus capital F of A, this expression here on our right-hand side, and we divided it up into n terms. We used a mean value theorem to represent our n terms differently. We used that notation, which changed our f to our capital F to a little f, capital F prime to a little f. We rewrote all these terms as delta x's. That got our capital F of B minus capital F of A to this set of n terms added together, and then we wrote that in the summation notation, and then we were there at our result as long as we recognized that it was what we had achieved was this, and it was okay then. What we had achieved was this, and it was okay to take the limit as n goes to infinity because there was never any restriction on n in anything that we did. And then finally we did an example problem doing it the short way, we found the antiderivative of x squared, and that was x cubed over 3, and then we plugged in 0 and plugged in 2, got a result of 8/3. That's the same result we would get if we used the limit definition, but this way of doing it is a much, much faster way of doing it. And then the final thing that we noted is that we can't always find the antiderivative using, or here we gave an example of a function, a pretty simple looking function, whose antiderivative we can't find, and then we have to, in that case, revert back to using this method, this computer lab method, where we find, as we put it, lots of terms to give us good accuracy. So this concludes this video where we've proven the first fundamental theorem of calculus and showed an application problem. In the next video, we're going to actually show how to find this limit and get the answer 8/3, actually setting it up as a Riemann sum problem and finding it that way, just as one way to show that what we proved in this theorem is the same. So we're actually going to go through and show this part of the result. We're going to show that this limit can actually be found. It's very difficult to find in general, but we're going to show it in this specific case of the x squared between 0 and 2. So that's the end of this video. Take a look at the next one to show how to get this limit, get the area using the limit definition, the limit way of finding it.